The first phenomena we're going to look at that involves induction, as this phenomena is called, is simply thinking about a moving conductor. So we're going to simplify this as much as possible. We're going to think about a rectangular conductor, and we're going to have a uniform magnetic field. So notice that in this situation, our magnetic field is into the page, and the velocity of the conductor is to the right. So something to be careful about here is that initially we are not talking about any current whatsoever. We are simply taking a chunk of metal and making it move to the right. The other thing is, note that we're saying it's a conductor. This does not need to be a magnetic material. We're not talking specifically about iron. We could be talking about aluminum or copper. And in fact, because iron has its ferromagnetic interaction with the magnetic field, when we talk about induction, we don't talk about magnetic materials. We talk about, again, aluminum or copper, so that we don't need to think about the ferromagnetic properties. So we're excluding ferromagnetic properties from our discussion for the sake of simplicity. So now remember that in our conductor, you have a bunch of positives and negatives, not necessarily in a pattern per se, but just there are charges. Overall, your charge is neutral, but there are charges in it. Now again, our charge carriers are actually electrons, but to think about this scenario, it's going to be easier to think about it as if we think about positive charge carriers. So we're going to talk about positive charge carriers for simplicity, and again, the physics is still going to work out. So we think about our charge carriers, which is in the block that is moving to the right. So we then use V cross B to get our force, right? Remember that we said our magnetic force on a charged particle is V cross B, where you take into account the Q, and we'll talk about positive charges for simplicity. So V is to the right, B is into the page. That gives us a force that is up, which is exactly what you see here because it's a positive Q. Now in this case, they are perpendicular. So once it's perpendicular, it simplifies to this, right? So notice that you have a 90-degree angle between those things. Again, it doesn't have to be that way, but that will simplify our analysis. So positive charges then experience a force upwards. And if we treat them as our charge carriers for simplicity, we then say they move up. So our positive charge carriers are going to move up. Our negative charge carriers, you just flip this Q around because they're also moving to the right, and then they move down. So simply by taking a neutral conductor and having it move at a constant speed for simplicity, in our magnetic field, we get a charge separation. And notice that the charge on the top, right, we have positive Q on top, must balance the charge on the bottom because your entire object is neutral. This then looks kind of like a parallel plate capacitor, doesn't it? And hence, we can say that there's going to be an electric field in the conductor, which we will approximate to say it's uniform. That's not exact. Obviously, this isn't exactly a parallel plate capacitor, but for doing our analysis, we'll think about it as uniform. So as you get more and more charge separation, you would have a larger and larger electric field. But eventually, something happens. So this is our second picture from before. So you get more and more charge separation until your electric force balances your magnetic force. So remember, this magnetic force is what was driving that separation, so there was a net force. But now you have an electric field, so your positive charges are actually repelled from the top. So a positive charge would experience a magnetic force pushing it up, but it's going to experience an electric force from the charge separation already there, driving it down. At this point, when those forces are equal, there's no net force, and you no longer have a charge separation. So the idea being that simply by making this neutral conductor slide to the right, you separate charges, and at some point that phenomena stops. There's a maximum charge separation you get, because at that point individual charge carriers experience no net force. So what's helpful is we're only going to think about the situation where you've reached this final value, so we know that these forces are going to be equal, that represents our maximum charge separation. And this process from going from some charges separated to maximum charges separated would be very, very fast. So we can always analyze this situation. So what's going on here? Well, we actually are going to get a potential difference. Why? Well, we have an electric field over a distance. So think about your parallel plate capacitor. All you have to do to get the potential difference from a uniform electric field is multiply that electric field by the length. So we're going to say that the length of this metal, notice that this is the length perpendicular to velocity and also perpendicular to our magnetic field. So there's a direction perpendicular to both B and V. That is the length we care about, not whatever length. There's a specific length. So we're going to call that L. And so then in this case, you multiply your electric field, which is simply V cross B. And all that's coming from is saying that the magnitude of our electric force needed to be equal to the magnitude of our magnetic force, because net force equaled 0, and this is QE, and this was QVB. So notice that Q itself actually falls out, which is how we get this. So again, this has made the assumption that everything is perpendicular here. It doesn't have to be, but again, it simplifies our analysis to think about the situation in this simplified case. So then we multiply V times B, which was our E, by L to get our potential difference. So the takeaway of this is that we take a neutral conductor, it moves, and we'll talk next about why, but it moves in this magnetic field at a constant speed. You get a potential difference between the two ends. Now, this might remind you of the Hall effect, and it is similar to a Hall effect, but the Hall effect actually was using a current, where now we are grabbing our conductor and moving it. So there's a similar aspect to the Hall effect in that you're getting a potential difference that's perpendicular to two other things, but the Hall effect has to do with current, and this has to do with simply the metal itself moving. So here we've gotten a potential difference without a battery. So the important takeaway is that this is called motional EMF, and the reason for that is we called this potential difference from a battery our EMF. And this had to do with chemistry, right? The reason that you have a potential difference in a battery has to do with chemistry, and you have a chemical force doing work to separate charges. Now, instead of it being chemistry, you actually have the magnetic field, kind of. You have a magnetic force that is doing work to separate the charges. So we call it motional EMF to make it similar to a battery, but it's now a magnetic force that separates the charges rather than chemistry that separates the charges. So EMF in both situations is going to give rise to a potential difference between two ends. You can then imagine if you connect it by a wire, we know that current would flow from the battery. And so similarly, if we now connect this by a wire, current will flow. And that's the next video.